Lesson on continuous probability review. Again, we're going to just talk about continuous probability models and sort of see how that all works out here. So let's start sharing our continuous probability review. Okay, so remember before we talked about discrete random variables, what they do is they assign a number to every outcome in the sample space, and you can sort of see what I'm reading right here. What continuous random variable does is it's a random variable whose value can be any number on an entire interval on a line. And it gets hard to put a probability mass on a continuous random variable because there's an infinite number of numbers in between any two number that you can pick out on an interval on a number line. So it gets hard to actually sprinkle you got one probability. You got a probability of one that all of these things must add up to, and it gets hard to try to put it on a number when there's an infinite number of numbers in between any two numbers you can think of. So what we end up talking about is instead of probability mass function, we end up talking about a probability density function, and we'll see sort of an example of that here pretty soon. So the next part at least that we want to talk about is well, we just go through an example. So let's do an example. Suppose we wait on a train to get to our work every day, and it leaves exactly every 5 minutes. So regardless of what happens, every 5 minutes, bam, your train, in 0 seconds, and this train takes off. And then further suppose that, I don't really care about how long I have to wait. So I just sort of randomly show up to my train station. And so the question is, what is the probability that we have to wait for more than 2 minutes? So in order to figure out this probability, let me push this down a little bit. What we're going to do is define a couple random variables. And so I'm going to let the first random variable, x, be defined as exactly what you probably would think, right? So the amount of time and we're going to let that be in minutes that we wait for the next train. All right, and I'm going to find another random variable. We're going to call this guy y, and we're going to let it be the number of minutes. Let's see, maybe we can round this one up. Rounded up that we wait for the next train. Okay, so I claim that maybe one of these guys is a continuous random variable and one of these is discrete. And so you can probably note which one's continuous. This one is a continuous, and this one is a discrete. Why is it discrete? Well, let's talk about what the support is. So what is the support for this guy here? We can nail down what the support is for this random variable. I can either way, if it's rounded up, I'm always going to wait at least 1, 2, 3, 4, or 5. So our discrete version of this is some number 1, 2, 3, 4, or 5. The continuous one, what's our support for x? Support for x. That is going to be any number between 0 and 5. In other words, I could have 0.123, I could have 0.7, I could have any number that's that's on that number line. And the problem with, well, we'll talk about the issues later on when we get to why is it called a density function. I sort of threw that out there at the beginning, but we'll talk about that more in detail. All right, if that's the case, then we can certainly come up with a PMF. So a PMF for y, if you recall. So if this were y, then this would be the probability, or P of y, which would be the probability the random variable y is equal to just some small y, right, being that the small y. And the numbers that we could have is a 1, a 2, a 3, a 4, or a 5. And the probability, we're just going to assume that we randomly come out there, and that this happens 1/5 of the time, this happens 1/5 of the time, and so on and so forth. So that they add up to 1. What does that look like in terms of our, if I was going to draw this thing? So let's add a shape. We're going to add one of these guys. And remember what this looks like from last class. Let me move it around a little bit. And so maybe 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And maybe this is our 1/5. And if I was going to put a rectangle on here, let's see if I can do this with this. All right, and then let's see if we can copy this. Copy, paste. I can put it right there. Paste. All right, so we should see 1/5. Move this around. Paste. Yes, I know I'm talking for every little thing that I do here. It's kind of weird talking to yourself. And so that's visually what the PMF for Y looks like. Okay, so that's PMF for Y. So that's what we've already talked about. Now let's go back to our continuous random variable, which is the topic for today. How would we write what would the PDF of Y look like? So the PDF, remember this is a probability density function. It's no longer a mass, it's the density function. So what would that look like if I had to draw it? Let's put in another graph here. And then let's see, another 1, 2, 3, 4, 5. And then I'm going to go up to some, I don't know what C is yet, but we'll sort of figure what that is here in a second. So if I were going to graph this PDF, it would look, and this is supposed to be a straight line. It's probably not the straightest line that I've ever drawn, but again, I'm getting used to this thing. So it comes up, and this is supposed to be a rectangle, right? Because we got a 0 here, and the question is, well, how high does this thing go up? What is the probability underneath this curve here? It's like, so I'm going to let this be the curve. A straight line is a curve, some constant, if you will. We know that this is 5, so it's a length of 5. So the question is, well, how much, if this in here is a probability equals to 1, so the area underneath this curve has to equal 1, then what is my value for C? Let's see, so 5 times C equals 1, so C must be equal to 1/5. So our constant here is 1/5, and it sort of looks like our previous, right? So 1/5 here, you add up all those suckers, you get 1, and you add up all of the probability that's underneath this curve, and you also get 1. So how do we write it? Let me come over here. So how do we write it, right? So before, you might remember that it looked like this piece right here, right? So how did we write it before? Well, we kind of had some table, and you put the support down, and then you put the probabilities underneath them. Well, how do we write? This is now going to have to be a function. So I'm going to let this be f of x, and that's going to be equal to some c. In this point, it's 1/5. So we're just going to let this guy be 1/5. And when is it equal to 1/5? Well, it's not before 0. It only starts being 1/5 from 0 to 5. So this is 1/5 if x is between 0 and 5, and it's 0 otherwise. So this means otherwise. It allows me, so I don't have to do the x is less from -infinity up to 0, and so this allows me to sort of shorthand that. We've already found the value of c, right? Because we just used the fact that we know what the probability is underneath the curve, and I know if this guy's 5, then this one must be 1/5 in order for the multiplication to work out, right? So we know what that looks like. Why is it called a density function? So that's our next question. Is, why is this a density function? Why is it called a density function? Instead of a PMF, probability mass function. So if I have exactly one of probability to spread around my support for the distribution, so that because there are an infinite number of numbers, between any two numbers on or within our support. Any two numbers in our support. It gets impossible to spread, and I'm going to put this in parentheses, to spread our finite probability. So the idea is we've created this thing called a density function instead. Now, what is a density function? You can think of it exactly like you think of it of your current. Let me remove that little line there. You can think of it like a regular little density function, right? So what would I need in a physical sense? So think of it the same way that you do a density of, I don't know, metals. Yeah, that's an easy one to remember. So metals, for example, iron versus aluminum. Well, if I told you the density of iron was some number, you wouldn't know what the mass was until you had some volume, right? So we need a volume in order to calculate mass. Calculate mass. So density times volume equals mass. And that's the same way we want to, so it's the same idea here. The same idea here. We need an interval instead of volume. To calculate a mass, a probability mass. this distribution, so let's just talk about this particular distribution. This distribution is called, the one that we were talking about up here, the one that looks like this, where it's just some constant, is called a uniform distribution. Because it has a uniform density, if you will, but it has the same probability between any two intervals of the same size, of the same length. So for example, if you had an interval that was 0.5, so if we had a 0.5 interval, you would get, so between 1 and 1.5 is going to give you the same amount of probability as 1.5, I'm sorry, yeah, 1.5 to 2. So that's the idea. That's why it's called a uniform distribution. So in our case, all right, if we're going to, so I'm going to answer the problem now. So we got x is a uniform 0, 5, and these are the parameters of the distribution. This is sometimes an A. You'll see some books write this as an A and a B. So this is a uniform 0, 5, and we want to find, if you go back and read the problem, we want to find the probability that we wait for longer than 2 minutes, and that's equal to 2. Which is 1 minus the probability that we are less than or equal to 2. So 2 different ways to find the same thing. All right, what does that look like? So that's the next question, is how would I, so let's go ahead and put the density function back out there. And 1, 2, 3, 4, and 5. We're at 1/5. Right, and if I'm trying to find this probability, what I want, oh, no, let's find this probability. What I want is, here, let me use a different color. I want this probability here. It's in the box. So P, what is that probability? Well, how do we find the area? Because really all we're talking about is the area here. How do we find the area underneath the curve? What we're going to do is the integral from 2 to 5 of my density function, right? So it's 1/5. So that's my density. But I'm not looking for the density, I'm also looking for the width. So an infinitesimally small width times my density gives me, density times width gives me mass. So these two together give me mass. And that's what I'm looking for. I'm looking for the amount of probability mass that lies in between 2 and 5. And this is a simple integral, right? So it's just 1/5 x evaluated from 2 to 5 is 1 minus 2/5 is equal to 3/5. So this is synonymous with the same answer we would have got if we would have looked for it from the discrete version, because I would have, well, it's the probability greater than 2, but it would have been 1/5 here, plus 1/5 here, plus 1/5 here, right? And that would have been 3/5. Now, is that always the case? Not really, but it just so happens to occur in this one. Okay, now why did I write this way of doing business? Well, This uses the CDF. So this idea uses the CDF. And that's really the next thing that we want to calculate, because the CDF in the continuous case actually is very helpful. So let's calculate a CDF. So now what we want to do is use the information that we have so far to capture or figure out what the CDF is, the cumulative distribution function. So with that being said, let's go ahead and write cumulative distribution function. And just like before, it's the same thing that we've done before in the discrete case. So CDF. And hopefully today we'll figure out, or we'll see why we use the capital F. Okay, in order to do this, we need to put in the PDF, because that's what we're going to use in order to capture this thing, is utilize the PDF in order to figure out what the CDF is. So again, 1 through 5, and we're using a really simple PDF right now just to give you to capture the idea behind it. So if this is the PDF, then what we're doing is we're saying, okay, well, there's some X value, and regardless of what the X value is, but there's some X that we're trying to find the probability of. So I'm trying to use this, and I'm trying to find this probability. So this probability statement is, just like it was last class, that the random variable X is less than or equal to some, and again, I always say some small x, it's the X that's on the number line here, right? So this is the X values, and this is your PDF, f of X, and then what we're doing is we're saying, well, give me the probability that's underneath, that's in that curve right there, all the way up to that particular point. Okay, so if that's the case, then we can calculate that, right? So we know that the probability of before, let's see, this is a 0. The probability of before 0 is 0. So there's no, I mean, I know that's not a great line or anything, but that's supposed to hit the 0 there. And we know this is just an integral from -infinity up to 0. Because we're about to put an X in here, I'm going to use a dummy variable. I'm going to use y dy. And so that's, ooh, my bad, hold on. Let's change out that 0, and let's make it an X. So f of y dy. And we know what happens before 0, so we know what happens from -infinity up to 0. The PDF is going to be 0 times the width, right, the infinitesimally small width, and summed all the way up, all of this is going to go to 0. And then plus, once we get to 0, we're going to go to some X, and it's going to be f of y. In this case, would be just 1/5. So it's 1/5 dy, and then we don't need anything else after that because we need to stop at X. So this is going to equal 1/5 y evaluated from X to 0. And this is what happens to your dummy variables. They get integrated out, and it's just left with 1/5 X is equal to, or again, just like before, capital F of X. The capital meaning that it's the integral of the small f here. And we use the small f here for the density function. Okay, so let's find out what happens when I put in, let's see, what was it? We were using 1 minus, so if I put in 2, right? So I was trying to find 1, hopefully we did the same thing we did before. So f of 2. And in our case, 1 minus 1/5 times 2 equals to 1 minus 2/5, which will equal 3/5. And I believe that's the same answer that we got before, which was 3/5. And it is, so we see that and it makes sense, right? Because we're doing exactly the same thing that we did before. We're just finding some function that does that instead of finding the actual number. All right, let's go back to the problem that we're doing here. So in order to find, well, I guess what I'm interested in is now that we found the probability, the next thing you might be interested in is the expected value. So let's talk about how expected value is used. So expected value. let's talk about how expected value is used in this sense, or in the continuous sense, and what it really means. And I think the way that you can do that is using the discrete. So in the discrete case, it would equal to the sum over all the x's of x times p of x, where p of x represented our probability mass function, and we get something like that. So in the continuous case, so continuous, our expected value of x would equal, instead of a summation sign that you use in the discrete case, we would want to use the integral from negative infinity to infinity of x times f of x dx, where this p of x here is represented by this density function times your interval. And in our case, in this particular example, we would just get 0 to 5 is the only place where we have support for this distribution, and then it would be x times 1/5 dx, which would equal, what is that, 1/5 x squared over 2, 1/5 x squared over 2 evaluated from 5 to 0, which would be 1/5 5 squared over 2. One of those goes away, and we're left with what, 5/2. All right, so that's that guy. That's the expected value. And if we're going to use the shortcut formula, we know we need the expected value of x squared, and that's the integral from negative infinity to infinity of x squared f of x dx, which in our case, just from 0 to 5 of x squared, 1/5 dx. Again, we're trying to use a very simple PDF so that we're not really worried about all of the algebra and whatnot. So we know that would be x to the third, or even some of the calculus, right? So so we still have the 1/5 out here in front. We're going to take the integral, or the antiderivative of that gives us x over 3. You evaluate it from 0 to 5, and that is equal to 5 to the third divided by 3, and I still have a 5 underneath. I still have this 5 there. 3 comes over, 5 to the third, and then minus 0 to the third would go away. And that will go to 2, that guy will go away, and we're just left with 25 thirds. And this is the expected value of x squared. So if we want the variance, right, we got to remember the shortcut formula. And it's just the expected value of x squared, which we just calculated, minus the expected value of x quantity squared, which we just calculated, and we just substitute, right? So we take 25 thirds, and then we subtract 5 halves quantity squared, which would be 25 thirds minus, what is that, 25 fourths, which would be, let's see, let me use a different color here. This game, I'm going to go 4 over 4 and 3 over 3. And if we did that, we get so 12 on the bottom. So I got 12 on the bottom, and I got 4 25s minus 3 25s. So I'm just left with 25 on top. And that's our variance. Okay, next class we will talk about some, I guess what we need to do is start talking about the Poisson process. And so in order to be able to talk about the Poisson process, we need these ideas and then put them all together into the Poisson process, because we're going to start talking about Markov chains in the future. So I expect for us to do Poisson process and exponential distribution next. All right, till next time.